Quantum entanglement, a phenomenon at the heart of quantum mechanics, describes a profound connection between two or more particles where their fates become intertwined, regardless of the distance separating them. When entangled, measuring a property of one particle, such as its spin or polarization, instantaneously influences the state of the other entangled particle, even if they are light years apart. This immediate correlation has led to much fascination and, at times, misunderstanding, particularly concerning the notion of faster-than-light communication. Crucially, while the correlation between entangled particles is indeed instantaneous, this does not permit the transmission of information faster than the speed of light. The no-communication theorem, a fundamental principle in quantum mechanics, rigorously demonstrates that entanglement cannot be exploited for superluminal signaling. The reason lies in the inherent randomness of quantum measurements. Although the measurement of one entangled particle instantly determines the state of the other, the outcome of any single measurement is fundamentally probabilistic. An observer at one location cannot choose or predetermine the outcome of their measurement to encode information that would then be instantaneously revealed to an observer at the distant location. Both observers will only ever see a random sequence of measurement outcomes. It is only when they later compare their results, by classical means of communication, which are limited by the speed of light, that they can confirm the correlations predicted by quantum entanglement. The apparent spooky action at a distance, as Albert Einstein famously called it, arises because the entangled particles do not possess definite individual properties before measurement. Instead, their properties are interdependent and exist in a superposition of states until a measurement is performed. Upon measurement, the wave function of the entangled system collapses, and the definite states are realized for both particles simultaneously. This non-local correlation is a cornerstone of quantum theory, distinguishing it sharply from classical physics, where physical influences are always localized and propagate at finite speeds. The study of quantum entanglement continues to push the boundaries of our understanding of reality, with implications for quantum computing, quantum cryptography, and fundamental tests of quantum mechanics. It underscores the profoundly non-classical nature of the quantum world, where concepts like locality and determinism, intuitive from our everyday experience, no longer fully apply. The intricate nature of quantum entanglement continues to challenge our classical intuitions, prompting a deeper exploration into the very fabric of reality. One of the most significant implications of this phenomenon lies in its potential for revolutionary technologies. Quantum computing, for instance, harnesses entangled particles to perform computations in ways that are fundamentally impossible for classical computers. By utilizing the superposition and entanglement of qubits, quantum bits, quantum computers can process vast amounts of information simultaneously, offering the promise of solving problems that are currently intractable, such as breaking modern encryption or designing new materials at the atomic level. Beyond computation, entanglement is also the bedrock of quantum cryptography, specifically in protocols like quantum key distribution, QKD. QKD allows two parties to establish a secure cryptographic key with an unprecedented level of security, guaranteed by the laws of quantum physics. Any attempt by an eavesdropper to intercept the key would inevitably disturb the entangled state, instantly alerting the legitimate users to the intrusion. This makes QKD impervious to even the most powerful future computers, as its security relies on the fundamental principles of quantum mechanics rather than the computational difficulty of mathematical problems. Furthermore, entanglement plays a crucial role in the burgeoning field of quantum communication. Scientists are actively researching methods to transmit entangled particles over long distances, with the ultimate goal of building a quantum internet. Such a network would enable entirely new applications, including distributed quantum computing, highly secure communication across the globe, and even the ability to link distant quantum sensors to achieve unprecedented precision in measurements. While still in its nascent stages, the progress in establishing stable entanglement links over increasing distances, both through fiber optic cables and free space optical channels, including satellite links, demonstrates the immense potential of this technology. The ongoing research into quantum entanglement is not just about technological advancement, it is also about deepening our fundamental understanding of the universe. Experiments designed to test the limits of entanglement, such as those involving Bell inequalities, continue to confirm the non-local nature of quantum correlations, definitively ruling out local hidden variable theories that attempt to explain quantum mechanics through classical means. These experiments continually reaffirm that the quantum world operates on principles that are profoundly different from our everyday experience, challenging our preconceived notions of causality and reality itself. The exploration of entanglement thus stands at the intersection of fundamental physics and cutting-edge technology, promising both profound insights and transformative applications. The persistent enigma of quantum entanglement continues to fuel groundbreaking research and philosophical debate, particularly concerning its implications for the nature of reality and the limits of communication. One of the most intriguing aspects, often misinterpreted, is the apparent spooky action at a distance. While the instantaneous correlation between entangled particles seems to violate the cosmic speed limit set by light, it's crucial to reiterate that no information is transmitted faster than light. This distinction is paramount. The correlation is instantaneous, but the transfer of meaningful data is still bound by classical communication channels. Imagine two people, each with one of a pair of entangled coins. They both flip their coins simultaneously. If one person sees heads, they instantly know the other person also saw heads, regardless of distance. However, they couldn't have chosen to make their coin land on heads to signal the other. The outcome of each flip is fundamentally random and unpredictable beforehand. It's only after a slow, classical phone call that they can confirm the perfect correlation. The practical applications of entanglement are rapidly moving from the realm of theoretical physics to tangible engineering feats. Beyond quantum computing and cryptography, entanglement is vital for quantum sensing and metrology. By exploiting the highly correlated states of entangled particles, it's possible to achieve sensitivities and precisions in measurements that are unattainable with classical methods. This has profound implications for fields ranging from medical imaging and navigation systems to fundamental scientific experiments, such as detecting gravitational waves with even greater accuracy. Imagine using entangled photons to create incredibly precise quantum radars or to build atomic clocks that are orders of magnitude more stable, leading to improvements in GPS and scientific timekeeping. Furthermore, the study of entanglement is at the forefront of efforts to understand the very fabric of spacetime, particularly in the context of quantum gravity. Some theoretical frameworks, such as certain approaches to string theory and loop quantum gravity, suggest that spacetime itself might emerge from entangled quantum states. This conceptual leap proposes that the very geometry of our universe could be a macroscopic manifestation of microscopic entanglement. While highly speculative, such ideas highlight the profound and far-reaching implications of entanglement, extending its relevance from practical technological advancements to the deepest questions about the nature of reality. The journey into understanding and harnessing quantum entanglement is still in its early stages, promising continued scientific revelations and transformative technologies that could reshape our world. The scientific exploration of quantum entanglement continues to unveil its profound and sometimes counterintuitive nature, pushing the boundaries of our understanding beyond the macroscopic world we inhabit. One of the most significant theoretical contributions to comprehending entanglement's non-local character comes from Bell's theorem and the subsequent experimental verification of Bell inequalities. In essence, Bell's theorem posits that if a theory of reality relies on local hidden variables, that is, if particles possess predetermined properties before measurement, and influences cannot travel faster than light, then there are certain statistical correlations in measurement outcomes that should be observed. Quantum mechanics, however, predicts different correlations, which are experimentally found to be true. This means that either locality or realism, or both, must be abandoned at the quantum level. The repeated and increasingly sophisticated Bell test experiments, often using entangled photons distributed over significant distances, consistently violate these inequalities, providing compelling evidence against local realism and affirming the fundamentally non-local and probabilistic nature of the quantum world. Beyond the foundational aspects, the manipulation and control of entangled states are at the forefront of quantum information science. Researchers are actively developing techniques for generating, maintaining, and measuring entanglement with unprecedented precision. This involves creating various types of entangled systems, from pairs of photons and trapped ions to superconducting circuits and quantum dots. The challenge lies not only in creating these delicate entangled states but also in preserving their coherence, their quantum properties, from decoherence, which is the loss of quantum information due to interaction with the environment. Overcoming decoherence is paramount for building robust quantum technologies, as it directly impacts the performance and reliability of quantum computers and communication networks. The study of entanglement also extends to the realm of many-body quantum systems, where it plays a critical role in describing phenomena such as superfluidity and superconductivity. In these systems, large numbers of particles exhibit collective quantum behaviors that are inherently linked through entanglement. Understanding the entanglement patterns within these complex systems can lead to the discovery of new materials with exotic properties and to a deeper understanding of fundamental physics, like phase transitions. For example, researchers use entanglement as a metric to characterize different phases of matter, recognizing that the degree and pattern of entanglement can differentiate between ordinary and topologically ordered states. This interdisciplinary approach, merging concepts from condensed matter physics, quantum optics, and information theory, highlights the pervasive and central role of entanglement in contemporary scientific research, continuously challenging our classical worldview and opening new avenues for exploration. The intricate dance of quantum entanglement continues to captivate physicists and technologists alike, serving as a cornerstone for both fundamental scientific inquiry and the development of next-generation technologies. A particularly fascinating area of ongoing research revolves around the concept of entanglement distillation and purification. Since entangled states are incredibly fragile and prone to decoherence when interacting with their environment, they often degrade, becoming less pure or less entangled. Entanglement distillation techniques aim to take many weakly entangled pairs and process them to yield a smaller number of highly entangled pairs, effectively concentrating the entanglement. This is crucial for long-distance quantum communication and for building fault-tolerant quantum computers, as it allows for the recovery of high-quality entangled states from noisy channels. Another frontier in entanglement research involves its application in quantum simulation. While building a universal quantum computer is a monumental task, specialized quantum simulators, often employing entangled systems of cold atoms or ions, can be used to model and understand complex quantum phenomena that are intractable for even the most powerful classical supercomputers. These simulators allow scientists to mimic the behavior of materials, chemical reactions, or even cosmological events at a quantum level, offering insights into high-temperature superconductivity, exotic magnetic phases, and the early universe. By controlling and measuring the entanglement within these simulated systems, researchers can gain a deeper understanding of the underlying physics without having to build the actual complex materials or recreate extreme conditions. The very definition and quantification of entanglement are also active areas of theoretical research. While for simple two-particle systems measures like concurrence or entanglement entropy can quantify the degree of entanglement, for many body systems and mixed states, defining and calculating entanglement becomes significantly more complex. Developing robust and efficient entanglement witnesses, experimental tools that can detect the presence of entanglement without fully characterizing the quantum state, is crucial for practical applications. These theoretical advancements, coupled with experimental ingenuity, are continually refining our understanding of this unique quantum correlation, pushing the boundaries of what is conceivable in the quantum realm and paving the way for truly transformative technologies. The relentless pursuit of understanding and harnessing quantum entanglement continues to shape the landscape of modern physics and engineering. A particularly intriguing and somewhat speculative avenue of research explores the connection between entanglement and the very fabric of spacetime itself. Concepts within quantum gravity, such as the ER=EPR conjecture, propose a deep equivalence between entangled particles, EPR pairs, and wormholes, Einstein-Rosen bridges. While highly theoretical and still debated, this idea suggests that entanglement might be a fundamental ingredient in the emergence of spacetime geometry, implying that the connectedness we observe in the universe could be a macroscopic manifestation of microscopic entanglement. This line of thought pushes the boundaries of our understanding, suggesting that the seemingly abstract nature of quantum correlations might have profound implications for the large-scale structure of the cosmos. Beyond these grand theoretical considerations, the practical implications of controlling and distributing entanglement over increasingly vast distances are being aggressively pursued. The development of quantum repeaters is crucial for overcoming the limitations of photon loss in optical fibers, which severely restricts the range over which entanglement can be maintained. Quantum repeaters would act like classical repeaters but without measuring and destroying the quantum information. Instead, they would use entanglement swapping and purification techniques to extend the range of quantum communication networks, ultimately paving the way for a truly global quantum internet. This infrastructure would not only enable ultra-secure communication and distributed quantum computing but also facilitate a new era of distributed quantum sensing, where widely separated sensors could be linked through entanglement to achieve unprecedented precision in measurements across large areas. The very act of precisely measuring and verifying entanglement is another area of intense scientific focus. As quantum systems become more complex, with increasing numbers of entangled particles, the challenge of fully characterizing their entangled states grows exponentially. This has led to the development of sophisticated techniques like quantum state tomography, which aims to reconstruct the complete quantum state from a series of measurements. While experimentally demanding, such methods are essential for certifying the quality of entangled states in quantum devices and for validating theoretical predictions. The ongoing refinement of these measurement techniques is not just about technological improvement, it also serves to deepen our empirical understanding of entanglement itself, providing crucial data that continues to challenge and refine our fundamental theories of the quantum world. The exploration of quantum entanglement continues unabated, revealing ever more intricate layers of quantum reality and propelling us towards technologies once confined to science fiction. A significant area of ongoing investigation involves the thermodynamics of entanglement. Unlike classical information, entanglement is a resource that can be consumed or generated and even traded for other quantum resources. Researchers are developing frameworks to understand the energetic costs and benefits associated with creating, maintaining, and manipulating entangled states. This includes exploring concepts like entanglement work and entanglement cost, which aim to quantify the minimum energy required to establish a certain amount of entanglement. Such studies not only have fundamental implications for our understanding of quantum energy conversion but also practical relevance for designing energy-efficient quantum devices. Another cutting-edge aspect is the development of hybrid quantum systems, where different physical platforms are entangled to leverage their individual strengths. For instance, researchers might entangle photons, ideal for long-distance communication, with trapped ions, excellent for long-term quantum memory, or superconducting circuits, powerful for computation. These hybrid approaches aim to overcome the limitations of single-platform systems, paving the way for integrated quantum networks where information can seamlessly flow between various quantum devices, each specialized for a particular task. This interdisciplinary effort brings together expertise from quantum optics, atomic physics, condensed matter physics, and materials science, demonstrating the collaborative nature of modern quantum research. Finally, the philosophical implications of entanglement remain a vibrant area of discussion. The persistent non-locality, even after decades of experimental verification, continues to challenge our classical intuition about causality and determinism. Many worlds interpretation, Copenhagen interpretation, and transactional interpretation are just a few of the competing frameworks that attempt to make sense of the spooky action at a distance and the measurement problem in quantum mechanics. While these interpretations don't alter the mathematical predictions of quantum theory, they offer different conceptual pictures of reality, prompting ongoing debates among physicists and philosophers alike. The profound nature of entanglement ensures that it will remain a fertile ground for both scientific discovery and intellectual discourse for the foreseeable future. The scientific odyssey into quantum entanglement continues to deepen, consistently pushing the boundaries of what we understand about the universe and how we might harness its most peculiar phenomena. One particularly active area of research centers on topological entanglement. Unlike the more straightforward entanglement between a few particles, topological entanglement describes a more robust, non-local form of entanglement inherent in certain exotic states of matter, such as topological insulators and fractional quantum Hall states. This type of entanglement is highly resilient to local disturbances, making it exceptionally promising for building inherently fault-tolerant topological quantum computers. The information in these proposed computers wouldn't be stored in individual fragile qubits but rather in the global, topological properties of the entangled state, offering a pathway to significantly more stable and error-resistant quantum computation. Beyond the realm of exotic materials, the principles of entanglement are also finding fascinating applications in quantum biology. While still a highly speculative and emerging field, some researchers propose that quantum phenomena, including entanglement, might play a role in biological processes previously thought to be purely classical. Examples include the high efficiency of photosynthesis, where energy transfer might involve coherent quantum pathways, or the navigational abilities of birds, which could potentially rely on Earth's magnetic field sensed via entangled electron spins. While experimental evidence for large-scale entanglement in living systems remains elusive and highly debated, the theoretical exploration opens up intriguing interdisciplinary avenues, suggesting that nature itself might have found ways to leverage quantum mechanics for survival and efficiency. Finally, the study of entanglement is profoundly impacting our understanding of black holes and wormholes within the framework of theoretical physics. The firewall paradox and its proposed resolutions often involve intricate considerations of entanglement. For instance, the concept of entanglement monogamy, the idea that a particle can be maximally entangled with only one other particle, becomes crucial when considering how information might escape from a black hole or if it's lost forever. The AD/CFT correspondence, a duality between certain quantum field theories and gravitational theories, further reinforces the deep connection, suggesting that the geometry of spacetime on one side of the correspondence is intricately related to the entanglement structure of the quantum field theory on the other. These theoretical explorations highlight that entanglement isn't just a quirky feature of quantum mechanics but potentially a fundamental element in describing the most extreme and mysterious objects in our universe. The journey into the depths of quantum entanglement continues to reveal its profound implications across an ever-widening spectrum of scientific disciplines, from the most fundamental aspects of reality to the cutting edge of technological innovation. A particularly compelling current focus is the exploration of entanglement in quantum field theory. In this more advanced framework, particles are seen as excitations of underlying quantum fields that permeate all of spacetime. Entanglement in this context is not merely a relationship between discrete particles but rather a correlation between different regions of these quantum fields. This perspective is crucial for understanding phenomena in high-energy physics, such as particle interactions at colliders, and for grappling with the quantum nature of black holes and the early universe. The entanglement between different modes of quantum fields, for instance, is thought to play a role in the Hawking radiation emitted by black holes, linking gravity, thermodynamics, and quantum information in a deeply intricate manner. The development of robust and scalable methods for generating and maintaining multiparticle entanglement is another significant challenge and an active area of research. While creating entangled pairs, e.g., two photons, is becoming increasingly routine in labs, scaling this up to genuinely entangled states of many particles, e.g., hundreds or thousands of qubits, is extraordinarily difficult due to the rapid onset of decoherence. However, achieving such highly entangled states is indispensable for realizing the full potential of quantum computers and advanced quantum sensors. Current approaches involve meticulously isolating quantum systems from environmental noise, cooling them to extremely low temperatures, and employing sophisticated control techniques using lasers or microwaves. Breakthroughs in this area could unlock quantum computing capabilities far beyond what's currently imagined, enabling simulations of molecular interactions with unprecedented accuracy or the development of new materials with designer quantum properties. Finally, the study of entanglement also informs the critical field of quantum metrology and sensing. By leveraging the unique correlations offered by entangled states, scientists can achieve measurement sensitivities that surpass the fundamental limits imposed by classical physics, the so-called standard quantum limit. This Heisenberg limit of precision, achievable with entanglement, promises revolutionary advancements. For example, entangled photons can be used in quantum lithography to create finer features than classical light, potentially leading to more precise manufacturing processes. Similarly, entangled atomic clocks or quantum interferometers could dramatically improve the accuracy of timekeeping, navigation, and gravitational wave detection. The ability to manipulate and exploit entanglement for enhanced sensing is transforming fields from medical diagnostics to fundamental physics experiments, solidifying its role not just as a theoretical curiosity but as a powerful tool for pushing the boundaries of what is measurable and knowable. The relentless scientific inquiry into quantum entanglement continues to unravel its mysteries, expanding our comprehension of the universe and offering blueprints for technologies that seemed impossible just a few decades ago. A crucial area of modern research focuses on the certification and verification of entanglement. As quantum experiments become more complex and quantum devices approach practical applications, it's not enough to simply claim entanglement exists, one must rigorously prove its presence and quantify its degree. This is especially challenging for multiparticle entangled states. Scientists employ sophisticated mathematical tools and experimental protocols, such as entanglement witnesses and Bell tests performed on larger systems, to provide irrefutable evidence of entanglement, ensuring the integrity and reliability of quantum technologies. Beyond fundamental verification, the active manipulation of entanglement forms the core of quantum error correction. Even the most isolated quantum systems are susceptible to noise, which can destroy the fragile entangled states vital for quantum computation. Quantum error correction codes don't fix errors by measuring the qubits directly, which would collapse their superposition, but by entangling the data qubits with ancilla qubits in a way that allows errors to be detected and corrected without revealing the underlying quantum information. This field is paramount for building fault-tolerant quantum computers, transforming the raw, noisy qubits available today into reliable computational units. It's a testament to the power of entanglement that it can be used not only to store and process information but also to protect it from the very quantum noise that threatens its existence. Finally, the study of entanglement is extending into the realm of quantum biology with increasing sophistication. While still highly speculative, emerging theories suggest that quantum coherence and entanglement might play a role in biological processes previously thought to be purely classical. Examples include the high efficiency of energy transfer in photosynthesis, where absorbed light energy seems to navigate molecular pathways in a coherent, wave-like fashion, potentially exploiting entanglement to find the most efficient route. Another intriguing hypothesis involves the magnetic sense of migratory birds, where entangled electron spins in retinal proteins might allow them to see magnetic field lines. While direct experimental evidence of robust, long-lived entanglement in biological systems remains a significant challenge, this interdisciplinary field highlights the potential for quantum mechanics to explain the subtle efficiencies and mysteries of life itself, pushing the boundaries of what we understand about the universe, from the subatomic to the biological. The profound and multifaceted nature of quantum entanglement continues to drive scientific exploration, revealing ever deeper insights into the fundamental laws governing our universe and pushing the boundaries of what's technologically possible. A burgeoning area of research is the investigation of entanglement in complex quantum networks. As quantum technologies mature, the vision extends beyond isolated quantum computers or single communication links to interconnected quantum ecosystems. This involves understanding how entanglement can be generated, distributed, and maintained across a network of geographically separated quantum nodes, each potentially housing different quantum devices, e.g., a quantum memory connected to a quantum processor. Developing protocols for quantum routing and entanglement swapping in such networks is crucial for enabling distributed quantum computing and a truly global quantum internet, allowing for seamless quantum information exchange across vast distances. Another critical frontier is the exploration of measurement-induced entanglement. Traditionally, entanglement is thought of as something generated through specific interactions between quantum systems. However, recent theoretical and experimental work suggests that entanglement can also arise, or be significantly modified, purely through the act of measurement, especially in many-body quantum systems. This counterintuitive phenomenon challenges our conventional understanding of how entanglement is created and dissipated, opening up new possibilities for manipulating and engineering quantum states simply by carefully designed measurement strategies. Understanding these dynamics is vital for both fundamental condensed matter physics and for developing new control techniques in quantum information processing. Finally, the philosophical and foundational implications of entanglement remain a fertile ground for inquiry, particularly concerning the concept of quantum contextuality. Unlike classical physics, where properties of an object are assumed to exist independently of whether they are measured or how they are measured, quantum mechanics demonstrates that the outcome of a measurement can depend on the context of other measurements being performed. Entanglement plays a key role in demonstrating this contextuality, further reinforcing the non-classical nature of quantum reality and challenging our intuitive notions of objective properties. These ongoing debates are not merely academic exercises, they push the very limits of our conceptual frameworks, striving to build a more complete and coherent understanding of a universe where entanglement is not just a quirky feature, but a fundamental principle. The journey into the mesmerizing realm of quantum entanglement continues to unravel its profound secrets, impacting our understanding of the universe at its most fundamental levels and driving innovations that promise to redefine our technological landscape. A significant frontier in current research involves the exploration of entanglement in gravitational systems. While quantum mechanics and general relativity are notoriously difficult to reconcile, theoretical physicists are investigating how entanglement might behave in the presence of strong gravitational fields, such as those near black holes or in the early universe. This includes examining concepts like gravitational decoherence, where spacetime fluctuations could potentially reduce entanglement, and the role of entanglement in the information paradox associated with black holes. These highly abstract yet crucial investigations aim to bridge the gap between quantum theory and gravity, potentially leading to a unified theory of everything. Simultaneously, the engineering challenges of scaling up entangled systems are being tackled with increasing sophistication. Moving beyond small-scale laboratory demonstrations, researchers are focusing on creating and controlling large-scale entangled states, often involving hundreds or even thousands of quantum bits, qubits. This requires developing advanced techniques for quantum control and quantum error correction that can operate effectively on massive arrays of interacting qubits. Breakthroughs in this area, spanning superconducting circuits, trapped ions, photonic systems, and neutral atoms, are critical for building practical, fault-tolerant quantum computers capable of addressing real-world problems that are intractable for even the most powerful classical supercomputers. The sheer complexity of managing such highly correlated quantum systems demands innovative solutions in materials science, cryogenic engineering, and precise control algorithms. Finally, the philosophical and societal implications of a deeper understanding and eventual widespread use of entanglement are becoming increasingly apparent. The radical departure from classical notions of locality and reality forces us to reconsider our fundamental worldview. As quantum technologies, powered by entanglement, move from laboratories to everyday applications, questions arise regarding quantum security and ethical considerations. For instance, the absolute security offered by quantum cryptography could reshape global communications, while the immense power of quantum computing raises concerns about breaking existing encryption standards. The ongoing exploration of entanglement, therefore, is not merely a scientific endeavor, it is a profound journey that challenges our perceptions, promises technological revolutions, and necessitates careful consideration of its broader impact on humanity. The exploration of quantum entanglement continues its relentless march, pushing the boundaries of scientific inquiry and technological innovation in ways that are fundamentally reshaping our understanding of the universe. One of the most cutting-edge areas involves quantum networks and the secure distribution of entanglement across vast distances. Researchers are actively developing quantum repeaters that don't amplify signals in the classical sense, but rather employ sophisticated techniques like entanglement swapping and purification to extend the range over which fragile entangled states can be reliably transmitted. This is absolutely crucial for building a global quantum internet, which would enable not just ultra-secure communication through quantum key distribution but also distributed quantum computing, where multiple quantum processors could be linked together to tackle even more complex problems. A fascinating theoretical and experimental frontier is the investigation of entanglement in many-body quantum systems far from equilibrium. While much of quantum mechanics deals with systems in their stable, equilibrium states, understanding how entanglement emerges, spreads, and evolves in dynamic, non-equilibrium scenarios is paramount. This is directly relevant to fields like quantum thermodynamics, where scientists explore the interplay between entanglement, energy, and information in quantum engines and refrigerators. It also has profound implications for understanding complex phenomena in condensed matter physics, such as the behavior of quantum materials after a sudden quench or the dynamics of quantum phase transitions. Finally, the philosophical debates ignited by quantum entanglement remain as vibrant as ever, particularly concerning the very nature of locality and causality. The persistent experimental confirmation of Bell inequality violations means we must either abandon the idea that physical properties are predetermined before measurement, realism, or accept that influences can act instantaneously over vast distances, non-locality. This continuous challenge to our classical intuitions is not just an abstract philosophical exercise, it deeply informs how we conceptualize the fundamental building blocks of reality. As quantum technologies become more pervasive, these foundational questions will increasingly permeate public discourse, urging us to reconsider the very nature of information, interaction, and existence in a universe profoundly shaped by entanglement. The profound implications of quantum entanglement continue to expand, pushing the boundaries of scientific inquiry and inspiring groundbreaking technological advancements. One of the most active and exciting areas of research is the development of quantum repeaters. These devices are crucial for extending the reach of entanglement over vast distances, overcoming the inherent photon loss in optical fibers. Unlike classical signal boosters, quantum repeaters don't amplify the quantum state, which would destroy its delicate properties. Instead, they employ sophisticated techniques like entanglement swapping and entanglement purification to effectively stitch together shorter entangled links into longer, robust ones. This is a vital step toward building a truly global quantum internet, which would enable ultra-secure communication through quantum key distribution, as well as distributed quantum computing and highly precise networked quantum sensors. Beyond the realm of communication, entanglement is increasingly being explored for its role in fundamental condensed matter physics. Researchers are investigating how entanglement manifests in complex materials, particularly in exotic phases of matter like topological insulators and superconductors. Entanglement can act as a diagnostic tool, revealing the hidden order and collective quantum behavior that define these materials. For instance, the unique entanglement patterns in topological phases of matter offer inherent protection against local noise, a property that is being vigorously pursued for building inherently fault-tolerant topological quantum computers. Understanding and manipulating these intricate entanglement structures could lead to the discovery of entirely new materials with unprecedented electronic and magnetic properties. Finally, the philosophical questions stirred by quantum entanglement remain as compelling as ever. The persistent experimental verification of Bell inequalities forces us to confront the non-local nature of reality, the idea that a measurement on one entangled particle can instantaneously influence its distant partner, without any known classical communication. This challenge to our intuitive understanding of locality and causality continues to fuel intense debate among physicists and philosophers, driving the development of new interpretations of quantum mechanics. As quantum technologies become more integrated into our daily lives, these foundational questions about the nature of reality, information, and measurement will become increasingly relevant, inviting a broader public discourse on the profound implications of entanglement.